All right, continuing on with the multiple choice section. So we're back at this graph again, and we want to know what is the net displacement of the object from the time interval from 0 to 8 seconds. Just to be clear, displacement, if you really want to get it from a velocity graph, so from a position graph, it's final position minus initial position. When you have a velocity graph, so this is from a position graph, from a velocity graph, it's the area. And if you notice, we have a negative. I'm going to do this with a shortcut here because this is how we do multiple choice problems. I could do the area of this triangle here and the area of this triangle here and subtract the two since I have a negative area here. But let's note we go from 0 to 4 seconds here and 4 to 8. So what that tells me is I have a positive area here, a negative area here. They're equal, and so they actually end up canceling when you add them together. Now, for number 7. We have an object that's dropped from rest from the top of a 400-meter cliff, and we want to know how far it falls in 6 seconds. This is a distractor. We don't care how high up it is. We're interested in how far it fell. So I'm going to use the AP formula x equals 1/2 at squared plus v naught t plus x naught. And here I'm actually going to look at, what we could do is we could say that we start at 400 if you want. And then we'll get the final position, but then we're going to do one more step to get how far it falls. So x is negative 1/2, negative because gravity opposes the upward direction. It's in the opposite direction, it points downwards. Negative 1/2 times 10 times 6 squared plus 0 times t plus 400. So what I'm going to end up getting is negative 180 plus 400, and that ends up being 220 meters. So I started at 400. I wind up at a position of 220. So when I subtract these two, I've actually fallen 180 meters. If you want a visual picture, I'm at 400 here, and I wind up at 220 here. So I've fallen 180 meters. All right. So, the position of an object is given by the equation x is 3t squared plus 1.5t plus 4.5. X is in meters, t is in seconds, and we want to know when the net force on the object is equal to 0. So just remember, F net equals m times a. That's our entry into this. So really, it looks like they're asking me for something I can't solve for, but actually the little life hack here is, if we get the acceleration, then we automatically know what the net force is, even though we don't have m, because this is a little bit of a trick. We want to figure out when this happens. So we want to find the time when a equals 0, because when a equals 0, f net equals 0. So the first derivative is going to be 6.0t plus 1.5, and the second derivative is going to be 6.0 meters per second squared. And so what we realize is, since the acceleration is never equal to 0, the net force is never, ever equal to 0. All right, number 9. Oh, this is beautiful. Finally, something a little bit new. So the object falls as shown above, and we want to know which expression we use to obtain v of t. So if you remember, mg minus kv equals ma. And we have mg minus kv equals mdv dt. So let's see, we've got dt equals mdv over mg minus kv. I'm doing quite a bit of tricky quick algebra here. So dt over m equals dv over mg minus kv. Let's see which one of these matches. So I guess I'm going from 0 to t here, and 0 to v final here if I want to look at limits, but really what matters is what's in the integrand. So this doesn't seem to work. This doesn't seem to work. And then let's be really clear here. Mg minus kv dt with the dt over m. So which of the following expression can directly be used? We can't directly use this one. The only expression that's going to work for us, actually, is choice A right here. If you notice, they integrate from 0 to t here, so that's not going to work. So that's one of the small little things. So they do it as a definite integral, even though we did it as an indefinite. So The key here is you got to check your limits of integration. So that is a little calculus trick, a little something extra they've thrown into the problem. Regardless, you could have eliminated C, D, and E right away. And then the last thing is what's the difference between these two, and then you're expected to be able to look at the limits of integration and see that. That's actually something that's fair of me to expect of you, even if you haven't seen it before. So a 500 kilogram sports car accelerates uniformly from rest, reaching a speed of 30 meters per second in 6 seconds. During 6 seconds, the car has traveled a distance of. So let's figure that out. So first, v final is 30 meters per second, and I know the acceleration. I'm going to get the acceleration using v equals at plus v naught. So I have 30 equals a times 6 plus 0. So my acceleration is 5. And we start from rest, so let's get that distance that it travels. So we have x equals 1/2 at squared plus 0 plus 0. X equals 1/2 times 5 plus 36, because that's 6 squared. And so I'm getting 5 times 18. And I'm getting 90 meters worth of distance. So that's the next 5 problems, and we will go ahead and try to get through 10 through 15 in our next video.